Biostratigraphy is applied for several reasons in the industry besides just determining age. It's also a very valuable tool for understanding the depositional environment and the extent of your reservoir. It's helpful in correlating between wells. I have seen biostratigraphy be a very powerful tool for identifying subtleties in other data sets that may not be observed otherwise, and identifying geohazards. And also, I started developing it as a tool to aid in target characterization and to increase the success of drilling. So I'm going to show you a few examples related to these points today. First, I just want to familiarize you with the methodology of biostratigraphy in the industry, just in case you're not familiar with it. Samples are typically collected from cuttings at intervals of about 30 feet, typically 30 feet. We rely primarily on last appearance datums and ACMEs because reverse circulation drilling, which gives us the cuttings, can obscure first appearance datums. Counting methods are qualitative to semi-quantitative. More and more these days it's semi-quantitative. And a lot of folks use a variation of Mike Steisen's cascading count method. And this method is really helpful in identifying rare taxa. We're typically working in very deep wells and expanded sections. Wells can be 10 to 30,000 feet. I'm thinking particularly in the Gulf of Mexico since I'm down here in Texas. So that's pretty typical for the GOM. That's not going to be the same everywhere. And biostrat is not limited to nanofossils. Typically included are also foram and radiolarian data. Less often pali is included just because it's quite expensive to do. And here's an example of what one industry biostratigraphy chart might look like. This chart was made by Steisen and Jolly in 2008 when they were working at Shell. So this chart is public and available. Unfortunately, it was never published. But anyway, I know you can't read it. There's a lot of information on here, so I'm just going to zoom in on an area here that is for the nanofossils. And you'll see that the traditional nanofossil zones are over here on the left side. Shell came up with some of their own to fit better in the GOM basin particularly. In this column is absolute ages of the markers, and the markers, unless otherwise indicated, are assumed to be last appearance datums. And the point really to make on here is just to show the resolution that has been developed and is necessary to apply in these wells, where traditional nanofossil zones just wouldn't give us the resolution that may be necessary for understanding the stratigraphic section we're in. Biostrat data might look a little different if you're not familiar with it. It can look typical from just an Excel spreadsheet with your depths down the side, your species across the top, and your counts in between. More typically, it looks something like this, just tabulated data with your sample interval here, the species listed that were observed in that interval, and then your counts on the side. And there are a few special charting programs like BugCat or StrataBugs, and this is what the data looks like so that it can be used to chart in those programs. So just so you know what it might look like if you ever come across it, There might be some goofy extensions that you could look out for. And whenever I have the chance, I just have to make a point to say that a list of tops is not data. So if you go ask somebody for the biostrat data for a particular well and they just give you a list of tops, say, thanks, but can I also have the data? Because a list of tops is essentially an interpretation also, and this list can't be verified or improved upon without the original raw data. So that's all I'm going to say about that. All right, so with all that being said, I make these gigantic charts with as much data on them as possible, not just with microfossil data, but with other types of geological data. I know you can't read anything on this chart. That's kind of the point. There's a lot of information on here, and I'm going to break it down for you. So this is zooming in on the header. To date, this is the most comprehensive chart that I've made. So I've indicated with an asterisk the parameters that I include on all charts, and the other ones are just kind of bonuses on this one. So we start with scale, geologic age, electric logs, geophysical logs, pore pressure, fracture pressure. This is my favorite data to include with biostratigraphy, by the way. Then we have casing points, several columns for various types of comments. We have bathymetry, sample depths. Nanofossil data is in blue, foram data is in red, and over here on the far right are a couple columns grouping microfossils together that have particular environmental affinities that help with depositional environmental interpretation. So the next slide, I'm gonna focus in on this area here where I have the individual marker species listed. First of all, what you're looking at here is the scale. Comments are in here, sample depths. These first two columns are total nanofossil abundance. This column is on a normal scale, and this column is on a logarithmic scale. Sometimes we're working with such great numbers of nanofossils that it's hard to see the real pattern of the abundance on just a normal scale, as you can see the difference here. So sometimes we might be missing out on some information because we can't see it at a high enough resolution. So that's where the logarithmic scale comes in helpful. Then from there, across the top, I've got the marker fossils listed from youngest to oldest, from left to right. So if we are in a normal section, we should see a nice smooth downward trend from the upper left to the lower right. It's important and valuable to list the markers from youngest to oldest because it will help you see anything funny if you have reworking or if you have truncated section or something else. For example, this is a truncated section. So again, it's the same thing, scale, comments, total abundance, and then the markers. And we have 6 or 7 markers here that all truncated in the same sample. And you can also see this sudden sharp decrease in total abundance, which is an indication that something drastic has happened in a short amount of time. So what was interesting about this section was that until it was charted, this truncation of all these markers, this disconformity, wasn't detectable in the biostrat or in any other data set. Just reading through the data, one top was noted. And that was correct, except all these other markers topped out in the same section too. It wasn't identified by the paleontologists collecting the data. It wasn't identifiable by just reading through the data. And it's a mistake that anybody could have made. It's something that anybody could have missed, because at one point, all these markers do coexist. So it wouldn't stand out as anything out of the ordinary. But when we finally charted it, we saw this truncation. And why this was so important was because across this interval, our pore pressure jumped nearly 1 ppg in less than 200 feet, and we nearly lost the well. And it was because of this unconformable section. So being able to chart all of this data and get this visual helped us understand what was going on. And then this boundary was able to be identified in seismic and on logs, and then mapped so that it could be identified in the future and we could prepare for it better. We developed a couple of ways to interpret our depositional environment in the Gulf of Mexico. These two next slides I'm going to show you work particularly well in the deep water Gulf of Mexico. So these might not be applicable everywhere, but the general idea could be adjusted to work elsewhere. So here, to determine environmental stability, we grouped Eubogerina species together. Those are forams, infaunal benthic forams, that really like stable, established environments because they burrow just below the surface and just stick out here enough to grab their food. So they want stable grounds and clear waters. When we compare those with agglutinated forams, which are pioneering species that really thrive in unstable, turbid environments, we see a very clear and a very clear contrast. So we can see where our environment has gone from unstable here, filled with agglutinated forams that need this clastic input to build their tests, to an environment that stabilizes, and we see more of these Eubogerina. So that helps us understand our depositional environment better, and that perhaps can have implications for your reservoir too. Another thing we were able to apply was comparing reworked Cretaceous nanofossils to interneritic benthic forams. Again, this works in the deep water because neither of these should show up in a deep water well. Neither of these would be living there. So how did they get there once they were dead? So reworked Cretaceous nanos are being shed by the rivers from the hinterland and carried into the ocean. And interneritic benthic forams are being shed from the shelf, from the very shallow waters. And we think this gives us a little bit of an indication about sea level and where our sediment source is coming from. So maybe like river direction. Anyway, the idea would be that if we've got a lot more reworked Cretaceous nanos than interneritic benthics, we might be seeing lower sea level where the river is bypassing the shelf and depositing its load closer to our deep water well than in times of high sea level where the river is dumping out farther upshore, but now the shelf is susceptible to sediment shedding downslope into the deep water. So that was the idea. It seemed to work. We also made these big microfossil distribution charts. This one is actually foraminifera. Foraminifera are great environmental indicators. So what you're seeing again is depth on the far left and then total foram abundance. And across the top are all of the species that were observed in order of their appearance downhole. So you're getting a general picture of time. These distribution charts can give you a general idea of sedimentation rate, depositional environment, and help you identify additional disconformities or unconformities that might not be associated with markers that you might not be able to see on just a biostratigraphy chart. So a few things to point out on here regarding sedimentation rates. If you've got a steeper slope here, that's an indication of a lot of deposition over a short amount of time, so a high sedimentation rate. Conversely, a shallow slope like this indicates little deposition over a lot of time, so a lower sed rate. High fossil density, which would be indicated by all this blue over here, that indicates an environment of high productivity, high stability. Conversely, low fossil density, like down here, might indicate higher turbidity, higher clastic input, and less stability. For disconformable surfaces, I know it's small, but you can kind of see it here, this flat top. All of these species truncate at this depth on this surface. These sorts of patterns can be helpful when you don't have a marker. If you need more resolution, if you don't have markers, this sort of thing, this sort of signal and pattern can also be a helpful biostratigraphic tool. So I'm going to show you some examples of that on this slide. The scenario here is two wells that were drilled close to each other and cannot be geologically correlated by any other means. Initially, both of these wells appeared very stratigraphically dissimilar. And so after they tried everything else, they brought in the biostratigrapher to see what he could do with it. So actually my partner did this work, I did not. So he noticed that markers were present, but he couldn't rely on the first or last appearance datums because he quickly identified some major unconformities. So early on, he realized he needed to develop other biostratigraphic tools to have a chance to figure this out. So these colored lines across each chart indicate correlative biological events. He identified at least 3 major regional unconformities: the blue line here, this green line, and this yellowish line. He identified that these were correlative unconformities between wells because the assemblage patterns above each of them were similar. So what he did was gradually trimmed the section from well A, that taller section, to see if he could get it to match the section from well B, because theoretically they were drilled close together, so they should be correlatable. So he's making an effort here to trim well A to see if he can get it to match. So here's the original section. He trims off some excess that he didn't see in well B, so he gets here. Now he's trimming it down a little bit more to go from here to here. And then finally, he puts well A and well B back next to each other to see how similar they are now. And lo and behold, it pretty much looks like he's got the same section. Ultimately, well A was determined to be an expanded section of well B, And the shortening of the section in well B was due entirely to the unconformities. So using the identified unconformities and the patterns of abundance above each of them is what became the biostratigraphic markers in these wells and in all the other wells in the basin. And it proved effective in every single well. This is how everything finally got figured out. So just that to say that in the absence of traditional markers, there are still tools available to make biostratigraphy effective and useful and applicable. Finally, I want to give you an example of how we tried to develop biostratigraphy to be a predictive tool. The scenario here is that we were planning to drill a new well, subsalt, right next door to this one that you see the data for. The new well was expected to be very high pressured because this one was. The casing points were going to be set based on biohorizons. So we wanted to see, by integrating data, how we could use this previous well we had drilled as a guide for the new well. So again, what you're seeing here is the scale, the geologic age. We've got our electric logs here and the geophysical logs and the pore pressure. And then over here, you'll see the biostrat markers pop up. So the idea here was very simple. We just identified the biohorizons relative to the pore pressure to kind of tell us where we are along this pore pressure trend. So these two markers indicated that we were approaching a pressure ramp, that's pore pressure increasing here. The pressure ramp was associated with these two markers, which were also unconformities. So we would expect to look for these and understand that we're about halfway up this pore pressure ramp and we still have a ways to go. And then finally, we had two markers bracketing maximum pressure down here at this depth. So the idea there would be look for this marker, expect to be very close to reaching peak pore pressure, and then look for this marker and know that we're out of the woods and now pressure is going to start to decrease. So that was the idea. Unfortunately, the other well went completely sideways. It was not what anybody was expecting or predicting, and that was unfortunate, but also very interesting. So anyway, but this was the idea, and I really think that it could be a valuable tool when it has a chance to be applied some other time. So just to summarize, I went over some biostratigraphic methods used in industry, which are a bit different than those that are applied in academia. I went over a couple of techniques where I've applied biostrat in industry, and just want to make a point that these techniques are not limited to industry biostrat sets. They can be applied on any kind of biostrat data set. And the more data, the better. Ultimately, the goal in industry is to draw a comprehensive picture of the geology, because that is what's necessary to achieve success. So the more data you have, the clearer your picture will become, and no data set can stand well on its own. It all becomes better when they're integrated and they can be calibrated by each other. So with that, I want to say thank you. Thank you for listening. Thank you for your time. And I want to give a special thanks to Mike Steisen, who has been my mentor for the last several years and also a good friend. So thank you.